Team Acumentrics consists of 1 computer engineer, Corinne Ejemian, and 2 electrical engineers, George Acker and myself, Emil Jesmanssunde. We had the honor of working with 2 technical directors, Peter Uptek and Brendan Smearbeck. Acumentrics approached us and gave us the challenge of creating a battery management system for lithium-based batteries. A battery management system, or a BMS, is a system that essentially allows us to monitor and report critical information due to battery operation, and as well as protect the battery from any damage. Current BMSs are priced high because they are usually tailor-made for a specific application. And it's our task, or we are creating a system that is universally applicable to transform any regular rechargeable battery into a smart battery. Our system will increase the reliability as well as the life expectancy of the battery cell. Another key aspect is safety. We will provide protection due to dangerous voltage levels, essentially protecting the chemical structure of the battery. Our anticipated best outcome by May 2019 consists of 4 main categories. Our prototype will be able to monitor current, voltage, and temperature, as well as we want to protect and maintain our battery pack against dangerous voltage levels. We want to protect against overcurrent, overvoltage, and undervoltage. We also want to visualize our runtime characteristics, such as the state of charge, state of health, and estimated time remaining with the current power draw. Last but not least, we want our system to communicate through the SM bus communication protocol. This allows us to communicate with the battery directly. Our total system would also follow the Smart Battery Specification 1.1, which is the standard communication protocol for all smart batteries. As you can see, our total system is complex with a lot of advanced features, but we in Team Acumentrics embrace the challenge. And some of this challenge is already being solved, and Corinne is now going to talk about how to make this product a reality.
So over the course of the semester, we've accomplished many of the key aspects to our project. The core of the battery management system is the microcontroller. To meet our best anticipated outcome, the microcontroller must be able to convert DC voltage through multiple channels without drawing an excess amount of power from the battery or adding additional expenses. To meet this most anticipated outcome, we have chosen a microcontroller from the MSP 430 family that is low cost, low power, has analog to digital channels, and multi-function input and output pins. From programming with the microcontroller, we have configured our GPIO pins for channel sampling to make sure that our signals are working properly in programming and that they turn on. From here, we work on serial communication. Serial communication is going to mimic our SM bus protocol. As you can see here, we are able to output customized data to our host PC. Overall, this all ties into our analog to digital conversion to make sure it's working properly. We use a DC power supply to mimic the battery while the circuits are not yet available. All of this makes up the building blocks of our state of charge calculation. So state of charge is the capacity of the battery. If you look at your phone's the top corner, the battery percentage, the battery bar, that's the state of charge of your phone. So what you are looking at here is the Coulomb counting algorithm that we have implemented. We use Coulomb counting because it's low cost to our CPU. And Coulomb counting integrates current over a definite unit of time to add to the capacity of the battery. The way we approach this function is with a Riemann sum, where we use a slicing method to take intervals of current to add to our capacity of our battery. The more intervals that we take, the more accurate our state of charge calculation is going to be. So I just went over all the software aspects of our battery management systems, and George is going to go over what happens when the MCU turns off. How are we going to protect our battery?
On the electrical side, Emil and I have been heavily focused on researching and designing the different circuits that will define our BMS. We have designed these at the hardware level for our analog front-end circuits to protect against many different dangers to lithium-ion batteries. These include many different things, such as overvoltage, undervoltage, minimum undervoltage, and overcurrent. Without these types of protections, you could expect to see something like this.
Holy crap!
This is a lithium-ion battery venting from overcharge and over temperature. That can happen if you don't have these protections in place. To stop this, we have designed different circuits in Multisim to have fully functional simulations that protect against voltage signals that are too high or too low from our set parameters, and an overcurrent protection circuit which stops too high of current or a short circuit event from damaging our battery. To do this, we've chosen to use analog comparators to be able to set a reference so that no input signal will be outside of what we want to enter our system. In addition, we're using high power MOSFETs to be able to send those high power signals to ground and away from our sensitive components. This will protect the components, the microcontroller, and the battery cells and prevent damage from destroying the system. Finally, in our overcurrent protection circuit, we are capable of bidirectional current sensing to sense both on the charging and discharging ends of our battery system. In addition, we have chosen to design hydronation and wake on charger circuits to be able to supplement the analog front-end circuits. For this, in a minimum undervoltage situation, when the voltage of the battery drops below a certain point, we've chosen to design a circuit that allows the MCU to cut off power to itself and subsequently the rest of the system to prevent excessive discharge on the battery. A lot of you have seen something like this if you've ever seen this screen before. On the left, your phone battery has dropped so low that it can no longer power the entire system. But what if you want your phone to turn back on? By connecting a compatible charger to your phone can detect the charger and starts powering it again. Our BMS, through the use of our hibernation and wake on charger circuits, performs very similarly. When we reconnect a compatible charger to our system, it powers the BMS and subsequently all the protection functions. At this time, we've completed many different steps along our way to completing this project, but we still have a few challenges that lie ahead of us. These include the migration of our state of charge algorithm over to our MSP 430. Corinne already has a working Coulomb counting algorithm, as you saw, and this simply has to be migrated to the MSP for the final product. In addition, the SMBus communication interface must be designed onto the MSP for a final working product. On the electrical side, Emil and I need to design the circuit schematics from the simulations that we have already designed onto a circuit schematic software for the basis of PCB fabrication. From this, we can populate our boards and then perform different types of tests to ensure that everything is working properly. As you can see, we've completed many different steps along our way, and we've completed much progress on all of our accomplishments, and we believe that these far outweigh these small challenges that lie ahead of us. We would like to thank those that have helped us along the way. We greatly appreciate your support, and we'll continue to work hard on this project throughout the spring. Thank you.